Hey everyone, welcome back to Trigonometry. This will be lecture 5 of the course, and in this section we're going to look at yet another way to think about the trig functions, and that's what we mean by the unit circle approach. And we'll also look at a bunch of properties of the trigonometric functions. All right, so let's go ahead and jump into it. So this will be lecture 5, unit circle approach and properties. Okay, so for the unit circle, I think we've talked about this a little bit, but let's go ahead and level set. What do we mean by a unit circle? So a unit circle is a circle whose radius is 1. Okay, so i.e. a unit, a single unit. So the radius is 1, meaning the distance from the center of the circle to the circle's edge is 1 unit. Okay, so for a unit circle, the radius is r equals 1. And typically we'll represent the unit circle, I would say pretty much all the time, as having its center at the origin of the Cartesian plane as well. Okay, so you can think of a unit circle as just being a circle that's centered at the origin with a radius of 1. So like this point right here would be 1, 0. This point here would be -1, 0. Up here, of course, would be 0, 1, and then down here would be 0, -1. Right, so if you think of these as points on the unit circle. Okay, and then every point in between, obviously. Okay, so a couple of things to note. So first thing to note is that the radius is equal to 1. Second thing to note is that the circumference of, i.e. the perimeter of the circle. For a unit circle, what do we know? Well, we know that the formula for the circumference is equal to 2 pi times the radius, right? And then obviously if it's a unit circle, it's 2 pi times 1, and so the circumference is exactly 2 pi. Okay. So we know the radius of our unit circle is 1. We know the circumference of our unit circle is 2 pi. Now this circumference equaling 2 pi is nice because the length of the circumference, so the length of the circumference is exactly 2 pi, which is also the radian measure of the central angle. Okay. Right, so if I have an angle here, if I go all the way around the circle, theta is equal to 2 pi. We know that from our discussion of radian measure. Now it's also the case that the circumference is equal to 2 pi, so the distance around the outside is 2 pi as well. Right, and that'll be very handy. That's going to come in very handy. Okay, so let's talk about how we do trigonometry using the unit circle. Okay, and so let's imagine we have a unit circle here. And let's see if I can draw another decent one. Okay, so I've got a unit circle. And let's put a point on the unit circle. It doesn't matter where we put it. I'm going to put it here for convenience. We'll call it P, and we'll let the coordinates of the point be A, comma B. So A, remember, is the horizontal distance. It's the x-axis distance. It's the x-coordinate. And then B is the vertical distance. So this is just the coordinates of this point. Okay, so you can think of this as the x-coordinate here and the y-coordinate there. Right. So that's all that is. Now if I have some ray extending from the middle of the circle through the point P, then there's an implied angle here, right? This angle here, theta. Now, because this is a unit circle, the measure of this angle is going to be exactly the same as the measure of this arc length. Okay, so depending on how you want to think about it, that can be important. Okay. So given this kind of a drawing, let's go ahead and define what the trig functions mean in the context of this sort of setup. Okay, so this would be like a definition. Okay, so we're going to let P equals AB be a point on a unit circle. I'll say the unit circle. There's only one of them, isn't there? Okay, and then we'll let theta be the central angle, be the central angle between the x-axis and a ray intersecting P. Okay, so then the sine of theta is equal to b, i.e. it's equal to the y coordinate. The cosine of theta is equal to a, the x component, and the tangent of theta is equal to b over a. Right? And then the assumption here is that a cannot be equal to 0. Right? Just like before we saw with right triangle trigonometry, it's possible for the tangent to be undefined. Okay. Actually, no, we didn't see that. I'm sorry, we haven't seen that yet in right triangle trigonometry. We're introducing that here. Okay, so if this is sine, cosine, and tangent, then it's easy to imagine what the others are. Cosecant of theta is 1 over b. Secant of theta is 1 over a. And the cotangent of theta is a over b. Here, b is non-zero. And here, for the cosecant, b is non-zero as well. And for the secant, a is not equal to 0. So we've got to put those in there just to be safe. Okay, so this is how we define the trig functions in terms of a unit circle. Okay. So sine of theta is b, it's the y coordinate. Everything is just some combination of a and b. Okay, and we'll see in a second why this is what it is. But let's do some examples just to make sure we're comfortable just pulling values off of this a, b coordinate. Okay, let's do a few examples and then we'll break this down a little further. Okay, so first example. Let's find the 6 trig functions for theta if p is equal to -1/2 comma square root of 3 over 2. Oh, if p is, this point is on a unit circle. Is a point on the unit circle. Okay, right, so basically the exact same setup as what we were just describing. So we don't need a picture necessarily to use this definition, but just for context, -1/2 comma square root of 3 over 2 would be -1/2 on the x-axis and square root of 3 over 2 on the y-axis. So it's somewhere over here. And so not knowing what theta is, we can at least picture it as being somewhere over here. Okay. But really, to solve this problem, since we're given p and we're told that it's on the unit circle, we can really just kind of pull all the values right off of here. So the sine of theta, remember, is equal to b, which would be the square root of 3 over 2. Cosine of theta is a, and that is then for -1/2. And the tangent of theta is b over a, right? So that's square root of 3 over 2 divided by -1/2. So square root of 3 over 2 times, you can just flip this upside down, 2 over -1. And so it's negative square root of 3. So there's those three. And then, of course, the cosecant of theta is just the reciprocal of this. So it would be 2 over the square root of 3. And to rationalize, we better write 2 square root of 3 over 3. And the secant is the reciprocal of cosine, and so that's -2 over 1, or -2. Okay. So the only one that we have left to do is the cotangent, and that's really just b over a, or a over b, which is the flip of tangent. So you could think of it like -1 over the square root of 3. Right? If tangent is this, then the cotangent's reciprocal. So it'll be negative square root of 3 over 3 in the end. Okay, so we've got all of the 6 trig functions values here for this angle that results in this point P being on the terminal side of it. Okay, perfect. All right. We can use this definition of the trig functions to identify a handful of other really valuable angles. And so let's do that one quick. Let's find the values of sine, cosine, tangent for, say, A. The first one would be theta equals 0 degrees, which is the same as theta equals 0 radians. B would be theta equals 90 degrees, same as theta equals pi over 2 radians. C is theta equals 180 degrees, which is theta equals pi radians. And then the last one we'll do is theta equals 270 degrees, which is 3 pi over 2 radians. Okay. And so these would be like the quarters, right? So up to the top, halfway around, 3/4 of the way around, and then the whole way around. Okay. So let's do these quick. Now, the way that this works is if I'm interested in theta equals 0 degrees or 0 radians, then I just can pick a point that would lie on the terminal side of that kind of an angle. 0 degrees means it hasn't moved off of the x-axis. And so the best point to pick would be 1, 0. Right? So like your A is 1, your B is 0. Okay? And so then it's just a simple thing. Sine of 0 degrees is equal to B in this setup, which is, in this case, 0. B is 0. The cosine of 0 degrees is equal to A, which in this case is 1. And then the tangent of 0 degrees is equal to B over A, which is 0 over 1, so 0. Right, so the sine is 0 for 0 degree at 0 degrees, or 0 radians. Cosine is 1, and the tangent is also 0. Okay, so that's the first one, and all of these will follow the same pattern. So let's look at theta equals 90 degrees, which is pi over 2 radians. So we're going to pick a point on the circle at the top here, right? So this time we'll use 0, 1. 0 on the x-axis, 0 on the x-axis, 1 on the y-axis. Right? And so sine of pi over 2 is equal to B, which is 1. Cosine of pi over 2 is equal to A, which is 0. And the tangent of pi over 2 is equal to B over A, which in this case would be 1 over 0, which is undefined. Okay. So the sine and the cosine flip at 90 degrees. So between 0 and 90 degrees, sine went from 0 up to 1. Right? So that's why you get like a half in here, and square root of 2 over 2, and square root of 3 over 2. So it goes from 0 up to 1. Right? And conversely, cosine starts at 1 here, and then it goes down to 0 at 90 degrees. And then the tangent becomes undefined. Right? And what we'll see is that the tangent actually grows without bound up to pi over 2, and we don't really have good terminology for that in trigonometry. I'll wait till you get to calculus, but basically, well, we can say that there's an asymptote there. That'd be the best thing we can say, I guess. Okay, let's. What about C and D? So C we're looking for theta equals 180 degrees, which is pi radians. And so the point to choose there would be, of course, -1, 0. Right? And so the sine of pi is equal to b, which is 0. The cosine of pi is a, which is -1. And the tangent of pi is b over a. Right? In this case, 0 over -1. And so it's 0. And then finally, theta equals 270 degrees, which is 3 pi over 2. 3 pi over 2. 1.5 pi. Okay, so that would be down on this axis. And in that case, we're looking at 0, -1 as the ideal point. That would be the point on the unit circle. So the sine of 3 pi over 2 is b, which is -1. The cosine of 3 pi over 2 is a, which is 0. And then the tangent of 3 pi over 2 is b over a, which is -1 over 0, so undefined. Okay? Very good, very good. All right, and so if you use your unit circle, if you go out and look at your unit circle, we will have just knocked out 4 more exact values using this definition. So theta equals pi over 2, 0, pi over 2, pi, and 3 pi over 2, and technically 2 pi as well. So we got all of those. Okay. All right. All right. So what we're going to do next is so this definition that we've just talked about, what we've been using, is sort of, it appears to be kind of confined to just the unit circle. But this can actually be extended very easily to include points anywhere in the plane. And what is actually the case is that the unit circle is a special case of what I'm about to show you. Okay, so the unit circle definition can be extended to accommodate any point P in the plane, not just a point in the plane on the unit circle, but any point in the plane, period. Okay, and so we'll kind of set this up, but I want to kind of work at this from an example. So let's say we have our XY coordinate system here. So this is the x-axis and the y-axis. And let's mark off 1 and then 1, right? And so I'm going to put a point up here at 1, 1. Okay. And if I draw a ray up to that point, right? So I'm going to let this be my P here. This is P equals 1, 1. Now, this point P equals 1, 1 is not on the unit circle, right? So notice if I were to draw a circle here of radius 1, it would look like this, right? It would kind of go like this, and clearly this point P is outside of the unit circle, right? So this is like the boundary of the unit circle. Okay. But ignoring the unit, just the point here is just that it's not on the unit circle. But now let's think about this point P, and let's try to fit this into the definition that we just worked on, right? So what I'm going to do is I'm going to think of this as being a triangle, right? So I've got a right triangle here. Okay, I know this leg is 1, and I know that leg is 1. And I could easily figure out what the hypotenuse is, but if you look back at a previous lecture, you'll see that we did that already, and that's the square root of 2. Okay, and then we'll make this the angle of interest here. So what I really have here is a right triangle. And I've got 1, 1, square root of 2. There's my 90-degree angle. Okay, now from right triangle trigonometry, I can figure out what sine, cosine, and theta are for this triangle. And then I can take that and I can work that into the definition that we just came up with using the unit circle approach. right? And so this is a 45-degree angle that I've defined here. I didn't say that up front, but you can imagine if this is a 1 and a 1, that must be half of a 90-degree angle. And so this is the sine of 45 degrees. Right? We did this one previously. We know that that's the opposite over the hypotenuse. So opposite over hypotenuse. So it's 1 over the square root of 2. Okay. And from the definition of trig functions using the unit circle approach, we know that the sine it's defined to be b, just b if it's on the unit circle, but here it's actually something different. It's b over some value r. We'll see what r is. R is the hypotenuse. You can already see that, but we'll talk about what that means in general. The cosine of 45 degrees is equal to the adjacent over the hypotenuse, which in this case is adjacent, which is 1. Hypotenuse is square root of 2. So we know that that's equal to a usually, but we're going to put it over r. Okay, and then the tangent of 45 degrees is equal to the opposite over the adjacent, which is opposite is 1, adjacent is 1. And we know from the unit circle approach that the tangent is b over a. Okay. And so what we've just done here is we have kind of mapped this right triangle trigonometry approach onto the unit circle approach. So this is the unit circle approach here, and this is the right triangle approach. Right? This is how we think about it in terms of the right triangle. Here's how we think about it in terms of the unit circle. Okay. And so this r, as you can see, corresponds to this hypotenuse value in the right triangle approach. Okay, so let's go ahead and define this now. We're gonna use, this is kind of our motivating example, and I'm gonna come up with a formal definition for you here. Okay, so the definition for any angle in standard position, let P equals AB be a point on the terminal side of theta. Now notice it doesn't say let P be a point on the terminal side of theta on a unit circle. It just says, hey, it's any point on the terminal side of theta. All right, so if I've got, my P, so if P is here, it doesn't matter if I use, so here's my terminal side, right? It doesn't matter if my P is there, or if it's up here, or if it's further up. It doesn't matter where it is. It can be any point on the terminal side of this central angle theta that's in standard position. Okay, so for any angle in standard position, let P equals AB be a point on the terminal side of theta. So I've got some angle defined by the x-axis and some ray. P is any point on that terminal side. And then we're going to let R, which will be equal to x squared plus y squared, the square root of that, be the distance between P and the origin. Okay. Then here are the trig functions. So the sine of theta is equal to b. On the unit circle it was just b, but in general it's b over r. Now on the unit circle we said it was just b because r is equal to 1 in the unit circle. But now r can be anything because p can be on the unit circle, it can be outside the unit circle, it can be inside the unit circle, it can be way outside the unit circle. All we have to do is know how far from the origin p is, and that's this number r. You might recognize the Pythagorean theorem at work here. Okay, so that's the sine of theta. The cosine of theta is a for the unit circle, but in this case it's a over r. And the tangent of theta is b over a. So notice for the tangent, we don't care where r is. We just care about the two legs. We just care about b and a. And then, of course, the cosecant is r over b. The secant is r over a. And the cotangent is a over b. Okay. All right. So that's the definition in general. This is the most basic definition for the trig function you could possibly have. So this is the most straightforward approach you can have. Now, what is this r here? All right, let's just make sure we're clear on what r is. So if I have a unit circle, well, just any circle, sorry, it doesn't be a unit circle. If I've got some circle here, right, and I've got a ray extending out of the circle, and it intersects this arc somewhere, right? Now, if this is the point AB, then this distance here is A, and this distance here is B, right? And so I can think of this as, again, a unit, or as a right triangle. Right, and so this leg is A, that leg is B, and this leg here, remember this up here is P, and this down here is the origin, 0, 0. Right, and that's, if I want to know the distance between 0, 0 and P, which is what it says here in the definition, then I can use, just like you use the distance formula from algebra, or because this is a right triangle, I can just use the Pythagorean theorem, right? So if this is r, then r squared equals a squared plus b squared, right? The two legs, square them, add them together, you get the square of the hypotenuse. And so then I can just say r is equal to the square root of that sum, like so. Right? And so that's all r is. It's just the distance, right? It's how you scale the sine and the cosine and the cosecant, the secant, given an a and b that's further out off of a unit circle or inside of a unit circle, really close to the origin, perhaps. Right. So this r is basically a scale. That's how it kind of operates in this definition. It sort of scales these functions. Okay. So let's do an example here. Let's use this in a nice example. So we're going to let p equals 4, negative 3 be a point on the terminal side of an angle theta. Okay, we want to find cosine, sine, and tangent of theta. Okay, so we're not told the angle. We can obviously see that this is not going to be on the unit circle. It's x coordinates 4. It's way too big. Right, so we can draw a picture if we want. I always like to just draw the picture. So it'll be 4 over and 3 down. So 1, 2, 3, 4. 1, 2, 3. It's going to be down here. So the ray will look like this, and the angle, of course, is this. Okay, again, in this case, the picture doesn't really do much for us. We can find these values without seeing the picture, but it's useful to see it. So the sine of theta is b over r. Okay, and so b is negative 3. R is, we don't know yet. Let's figure that out. Actually, we should have done that first. First thing we need is the r. So r is equal to the square root of x squared plus y squared. And in this case, the x coordinate is 4, the y coordinate is negative 3, so this would be 4 squared plus negative 3 squared. And so that's 16 plus 9. So that's the square root of 25, also known as 5. That's our r. So r is 5. Right, so the distance from here out to this point here is 5. Right, and you can think of that as like the hypotenuse here. Right, it's like the hypotenuse, isn't it, of a right triangle. Here's one leg, here's the other leg, there's the hypotenuse. Right, so the sine of theta is b over r, which is negative 3 over 5. The cosine of theta is a over r. A is 4, so it's 4 over 5. And the tangent of theta is b over a, which is negative 3 over 4. Right, so here are the 3 values. And we could easily just flip these over to find cosecant, secant, and cotangent. All right. Very good. So that's the unit circle approach to the trig functions, right? So you start with the unit circle, and they can be very easily generalized to basically a point anywhere in the plane, not on necessarily on a unit circle. All right. Okay, very good. Let's shift gears now. So I want to shift gears and start talking about some of the properties of the trig functions now. We're going to start by just kind of an informal discussion about the domain of the trig function. So we'll get into the domain with more rigor later when we start graphing the trig functions, but I just want to just introduce this idea a little bit before we get fully into graphing them. Domain of trig functions. Well, and the range. Well, I'll start with just domain. Okay, so what is the domain of a function? Well, loosely speaking, you can think of the domain of a function as being all of the values that you can legally, in air quotes, legally, plug into the function. All right, these are all the values that I can plug into the function without causing some kind of a situation where I've got an undefined value, or maybe the non-real numbers like square root of negative numbers, for example. Right, and so let's talk this through for the sine. So the definition of the sine of theta is equal to b. Right, and so b can be any number. Right, it's literally whatever b happens to be. That's the value of the sine function. So that being the case, the domain of sine is all real numbers. You can plug any number you want into the sine function and it works out, as long as it's a real number, right? Any real number. The same is actually true of the cosine, right? By definition, the cosine is just a, so I can plug in any angle I want. So the domain of the cosine is also all real numbers. So what about the tangent? Well, we know tangent generates undefined values occasionally, right? So tangent can generate undefined values. So tangent, I'll just say it this way at first, is sometimes undefined. Now, more specifically, when a is equal to 0. So when is a equal to 0? Right? When is a equal to 0? Well, you can think about it like this. The tangent of theta is equal to the cosine of theta over the sine of theta over the cosine of theta. Right? And so there's a couple ways to think about it. One way to think about it is this way, to say that the tangent is equal to sine over cosine. Cosine, and cosine of theta equals 0 when, well, we just kind of saw this, when theta is equal to pi over 2, when it's equal to 3 pi over 2. If you look back at the previous example, you'll see that. And it turns out this can be extended, 5 pi over 2, 7 pi over 2, etc. right? So another way to think about it is the cosine is equal to this a, right? And so when is a equal to 0? Well, if I've got a point up here, right, a is 0 here, right? If it's on the y-axis, that means it's not moved off the x-axis, so it's 0, right? So for example, this would be 0, 1. That corresponds to pi over 2, 90 degrees. It's also 0 over here, right? So this would be like the point 0, negative 1, right? And what angle is that? Well, that's 270 degrees. 90 degrees is pi over 2. 270 degrees is 3 pi over 2. If I keep going around, I get this one, 5 pi over 2. If I keep going around again, I get this one, 7 pi over 2, and so on, right? I can just keep going around and around. And whenever I'm an angle that results in the terminal side being on the y-axis, then the tangent is undefined. So tangent theta is undefined when the terminal side of theta is on the y-axis. And that happens at these odd multiples of pi over 2. So this happens at odd multiples of pi over 2, right? So namely pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So the domain of tangent is all real numbers except for odd multiples of pi over 2. The domain of tangent, all real numbers except the odd multiples of pi over 2. Okay, so that's the domain of tangent. So obviously sine and cosine's domain is everything. Tangent is somewhat restricted by the fact that it's a ratio of sine and cosine, and everywhere cosine is 0, tangent is undefined, right? So if tangent's undefined, that means whatever value makes it undefined is out of the domain. Okay, very good, very good, very good. All right, what about the range of these guys? So what about the range? And again, we'll get into this in more detail when we start graphing the trig functions. But what about the range? Let's think about this. I don't want to draw the graph of the sine functions yet because we're not there. But let's just think about the unit circle for a second. All right, so at starting point here, and so we're going to denote this as cosine is the first coordinate and sine is the second coordinate, right? Remember, cosine is A, sine is B. So here at the when the angle is 0, cosine is 1, sine is 0. Right, now as we move up here, cosine starts shrinking from 1 down, and then it hits like a half, and then it keeps shrinking down to 0 up here, and sine grows from 0 up to 1. So up here it's exactly reversed. Right, and so a good way to think about it is at each point on here you've got some implied triangle, right? And this length here is the cosine, and this length here is the sine. Right, now as this triangle moves up, obviously the cosine is going to shrink. At the bottom here, the cosine is everything, it's 1. And then as it starts to move up, this horizontal section shrinks and shrinks and shrinks until it's vertical and there's no horizontal section, it's all sine. And then we move over here, and over on this side it's -1, 0. So the sine grows all the way, sine goes from being 1 all the way down to 0, and the cosine grows from 0 to -1. Right, again, picture a triangle in here. Here's the cosine. It's obviously negative. It's going in the negative direction. Here's the sine. Right, it's vertical. right? And as it flattens out, the sine will shrink down, the cosine will grow, okay, until it gets here, and here the cosine reaches -1, the sine is 0 again. And then down here, of course, it's back to 0 for the cosine, and the sine is -1. Right, so down here you can just picture, you know, a triangle again, right? So the horizontal is cosine, the vertical is sine, and it'll just do the same thing. Okay, and so what happens is the minimum value for sine is -1, and that actually is the minimum value for cosine as well. The maximum value of cosine is 1, and that's the maximum value of sine as well, right? So cos is at a maximum, sine is at a maximum, cos is at a minimum, sine is at a minimum, right, as it goes around the circle. So the range of cosine is equal to -1 to 1. Technically, this should be like this. It's the same for the sine. Okay. All right. All right. And I think I'll leave off the discussion of the other guys until later. We'll get into graphing, and then we'll have to explore all of these things in more detail. But it'll be much easier to visualize when we actually have the graphs of the things. So I'm going to wait until then. Okay. Now we're kind of on to properties of these things, right? So the first property was, of course, what's the domain or range of some of these. The next property is this property of periodicity. So a function is called periodic. It's called periodic if there is a positive number p with the property that whenever theta is in the domain of f, so is theta plus p, and the function evaluated at theta plus p is equal to f, the function evaluated at just theta. All right, so that is a very wordy description of periodicity. Okay. We'll break this down a little further and make it somewhat more straightforward. But we also would say that the smallest such p is called the period of the function f. Okay, so whatever this p happens to be, there may be many of them, whatever the smallest such p is, we call that the period. So it's sort of like when does it start repeating itself. Now, the easiest way to see this is just like take a simple function like the sine function. So the sine, and we're going to take the sine of 90 degrees. Okay, we know that the sine of 90 degrees is equal to 1. We just saw that, right? Now, I'm going to propose that p equals 360 degrees. And we can see then that sine of 90 degrees plus p, in this case 360 degrees, is also equal to 1. Right? So this is your f of theta plus p in the definition here. And this is your f of theta. Right? So they're both equal to 1, so they're equal to each other. Okay, so sine of 90 degrees equals sine of 90 degrees plus 360 degrees, which is actually sine of 450 degrees, so that's 1. Right, now the interesting thing is that I can now keep going. I can say the sine of 450 degrees, which is this guy, is equal to the sine of 450 degrees plus p, again, 360 degrees, which is equal to the sine of 810, which is also equal to 1. Right? Now, what am I really doing here? If you think about this from the context of a circle, what am I really doing? I'm just going around again, aren't I? Right? So here's 90 degrees. Sine is equal to 1 there. Let me just put 0, 1. I don't want to bring any more p's into this one. So there's 90 degrees. Then 90 plus 360 would just be like going like this, around, and then around again. All right, so that's 450 degrees. Again, we're 1, right? We're landing in the same place. Then if I want to go around again, right, that's 810. I can go around again, another 360. And every time I go around, I land in the same place, right? And that's what is meant by periodicity here. In the context of the trig functions, that's all that is happening. It's just going around until the values align again. Right? And so the sine function is periodic with period 2 pi or 360 degrees, however you want to think about it. So the sine function is periodic. Turns out all the trig functions are periodic, right? The definition, one of the definitions, is based on a unit circle, right? So obviously, as theta grows, we're going to start repeating ourselves, aren't we? That's more or less what periodic means. It means you're going to repeat after a certain period. You're going to go a certain distance, and then you're going to start to repeat yourself. And you'll go that distance again, and then you'll start repeating yourself again. You just keep repeating your values over and over again. Okay, and so the periodic properties are that the sine of theta plus 2 pi is equal to the sine of theta. The cosine of theta plus 2 pi is equal to the cosine of theta. And the tangent of theta plus pi, not 2 pi, note, is equal to tangent of theta. Right, so the sine and the cosine are periodic with period 2 pi, or 360 degrees. The tangent is also periodic, but it has a different period. Its period is pi, or 180 degrees. It starts repeating itself after 180 degrees. Okay, and then of course all of these guys are going to follow suit, right? So cosecant of theta plus 2 pi is equal to cosecant of theta. Secant of theta plus 2 pi is equal to the secant of theta. And the cotangent of theta plus 2 pi is equal to the cotangent of theta. So they all align. All right. These are just the reciprocals of these. So obviously, if these are going to start repeating themselves after 2 pi, then the reciprocal of these, namely the cosecants, will start repeating themselves after 2 pi as well. Okay. How can we use this, this property? Well, here's a great example. Let's find the exact values for part A would be sine of 420 degrees. Part B would be the tangent of 5 pi over 4. And part C will do the cosine of 11 pi over 4. So for A, what we can do is we can say the sine of 420 degrees. Well, I know that sine is periodic with period 360 degrees, right? So whatever this is, whatever sine of 420 degrees is, it's going to be equal to sine of 420 degrees plus 360 and 420 degrees minus 360. And so if I subtract 360, it makes it quite a bit smaller of an angle, and it's an angle I'm familiar with. So I know this is equal to sine of 420 degrees minus 360 degrees. And that is just sine of 60 degrees. And I can look that one up on the unit circle cheat sheet, and I can see that that's the square root of 3 over 2. Right? So remember this periodicity, I think we just wrote plus, but the angle can be negative, right? So here I'm adding a negative 360 degrees, right? And so you can subtract or add whatever the period is and get the same trig value. That's kind of the trick with all of these. So the tangent of 5 pi over 4, well, I don't know what 5 pi over 4 is, but I know the tangent is periodic with period pi over 2. So I could subtract pi over 2 from this. So instead of 5 pi over 4, let's go 5 pi over 4 minus pi over 2. And that gets me tangent of, be 5 pi minus 4 pi all over 2. So if I get a common denominator, multiply top and bottom by 2. Okay. And so then I get, that's equal to, let's see here, it's equal to tangent of pi over 4. Oh, sorry, this should be a 4 there. Sorry about that. Pi over 4. And so then I get, I can look that one up and see that that's equal to 1. Okay. All right. Actually, I think this should, sorry, I think I made a typo here. This should be 2 pi over 4. So that means 5 minus 2. So this is 3 pi over 4. Yeah, it's the same answer, though. Okay. And then part C is the, if we're looking for the cosine of 11 pi over 4, well, I have no idea what the cosine of 11 pi over 4 is. So let's try to shrink that angle down. Let's subtract 2 pi from it. Because cosine is periodic with 2 pi periodic, right? So I can subtract 2 pi without changing the value. So 11 pi over 4 minus 2 pi over 1. Right? And I get cosine of, let's see, 11 pi over 4. And multiply top and bottom by 4, I get 8 pi over 4. And so this is cosine of 3 pi over 4, which is negative square root of 2 over 2. You can just look that one up. Okay. And so this is real helpful because I can just, subtract off whatever the period is and get a simpler angle to look at. Okay, so very good, very good. Okay, and then I think the last property that we want to discuss here is the even-odd function, the evenness and the oddness of the trig function. So we may remember even functions are functions where the if I have f of negative x, if that's equal to f of x, right? If f of negative x is equal to f of x, then the function is called even. Odd functions are functions where f of negative x equals negative f of x. Okay, so for an even function, a great example is like a quadratic function like this, right? So f of negative x, so maybe that's over here, this would be negative x. You can see that that is equal to whatever this guy is over here as positive x, right? So this is an example of an even function. An odd function would be something like this, maybe a function that goes like this, right? Still symmetry, a kind of symmetry, but it's not a symmetry that results in this kind of a pattern, but instead it results in this kind of a pattern. So if this is negative x here, then f of negative x is down here, And if this is x over here, in order to make f of negative x equal whatever this thing evaluates to, we'd have to flip it down, right? So we'd have to flip it down here. And so this would be negative f of x. Okay. So this is like an even function. This is what they kind of look like. And this is an odd function. Okay. And it turns out that the trig functions all fall into these categories, even or odd. So the sine of negative theta is equal to negative sine of theta. Right, so it's odd. The cosine of negative theta is equal to cosine of theta, so it's even. And then the tangent of negative theta is equal to the negative tangent of theta, so it's odd as well. So the sine and tangent are both odd, and as you can imagine, so therefore are cosecant and cotangent, since they're just the reciprocals. And then the cosine is even. Okay, so I'll write over here, so is cosecant of theta, and so is secant of theta, and so is cotangent of theta. Sine is odd, cosecant is odd, tangent is odd, cotangent is odd. Cosine and secant are even. Okay. And again, this will be very clear when we get into the next couple chapters where we talk about the graphs of these functions. We'll see why this evenness and oddness, we'll see where it comes from. Okay, so an example of how this can be useful, a couple of examples. If I want to know the sine of negative 45 degrees, well, that's not something that's explicitly written on our reference sheet, but I know that the sine is odd, so I know that sine of negative 45 degrees is equal to negative sine of just 45 degrees. And I know the sine of 45 degrees is square root of 2 over 2, so that means the sine of negative 45 degrees produces negative square root of 2 over 2. Okay. And then another example, the cosine of negative pi. Well, cosine is even, so I should put this on here. That one was odd. Cosine is even, and so that means that the cosine of negative pi is just equal to cosine of pi, which I know is negative 1. Okay. You can just look it up. The tangent of negative pi is equal to, it's an odd function, right? So it's equal to negative tangent of pi, right? And I know that the tangent of pi is 0, so this is negative 0, so just 0. Okay, what about this one? What about the tangent of negative 37 pi over 4? Well, first of all, let's get rid of the negative. Right, so tangent's an odd function, so I can write this as negative tangent of 37 pi over 4. What about this 37 pi over 4? Well, let's use the fact that tangent is periodic with period pi. So I can rewrite this as negative tangent of 37 pi over 4. Now, how many pi's do I got to subtract off of this thing? Well, if you take 37 divided by 4, that's 9 and some change, right? So I could subtract off 9 pi here, right? So subtract off 9 pi right? And that's going to be, let's do the actual math here, 37 pi over 4 minus, now 9 pi becomes 36 pi over 4. Right, when I get a common denominator, this is really 9 pi over 1. And so then this is equal to negative tangent of 37 pi over 4 minus 36 pi over 4. That's just pi over 4. Which we know is the tangent of pi over 4 is just 1. And so the answer is negative 1. Right? So you can see how you can take a really big, arbitrary, messy number like this, angle, an angle that you definitely are not going to find in your reference sheet, and using even odd properties and periodicity, you can just kind of reduce the angle or reduce the problem to a very manageable angle. Pi over 4 is an easy angle. We know that one. We can look it up. All right. Very good. All right, I'll leave it there. That'll be it for this section. And when we get together again, we'll start looking at additional properties of the tangent, or sorry, additional properties of the trig functions, and we'll get into some of the graphs of the trig functions as well. All right, take care, and we'll talk to you all later.